A sample optimization problem involving trig. The slant height S of a right circular cone is the length measured along the cone from top to bottom. So this is S. The volume of a right circular cone with a vertical height, which is this, of H, and a base radius, which is this, of R, is given by V equals 1/3 pi R squared H. If the slant height is fixed at S equals 10 centimeters, what is the angle that maximizes the volume? So, obviously our problem right now is that we don't have the angle at all, and we need to get that into the problem. So we're going to use that right triangle over there, and we're going to do some trig and say that R over S is clearly the adjacent over the hypotenuse, so that's going to be the cosine of our angle, theta. And then likewise, we can see that H over S is clearly just the sine of our angle, allowing us to solve these over instead to say that R is S cosine theta and H is S sine theta, and therefore V is 1/3 times pi times S cosine theta all squared times S sine theta to the first power. And therefore V can be written as 1/3 pi. We get an S cubed, and then we get cosine squared of theta, sine of theta. To get the maximum volume, we're going to have to take the derivative of this and find where it's equal to 0. So our goal is to take dV d theta over here. The stuff in orange is just a constant, and it will just come outside. It's basically just scaling the volume and plays no role for where theta is. And then we have a product rule. We have cosine squared times sine of theta. So when we take product rule, we end up with the derivative of the first, which is 2 cosine to 1 less power times the derivative of cosine, which is minus the sine, times, of course, the second. And then we add to that the first one, cosine squared theta, times the derivative of the second, which in this case is just cosine theta. This can be simplified a little bit, so we carry the constant because it just comes along for the ride. And then we have, in our first term, we would have minus 2 sine squared theta cosine theta, and in the other term we'll have cosine cubed theta. To optimize, we want to find the theta where this is, right? We want to find theta such that dV d theta is 0, which means really we just force it to be 0. So we say 1/3 pi s cubed times cosine cubed theta minus 2 sine squared theta cosine theta equals 0. I just slipped the order because it's usual to not have a minus something plus something else. It has absolutely no significance. The first thing we'll do, of course, is just cancel out, divide out the constant, and we'll have cosine cubed theta minus 2 sine squared theta cosine theta equals 0. Because a constant is a constant, it's non-zero since s is not 0, and we can divide it out and just get rid of it. And then we'll do, as we often do these kind of tricks, we will pull out 1 cosine theta, since it's in both terms, and that will leave us with a cosine squared theta minus 2 sine squared theta. And of course that still equals 0. The reason for doing this, of course, is that we can now use the factor property and say that if two things multiply to 0, then one or the other is 0. So we know that either this is 0 or this is 0. So we just tackle those separately. Let's begin with whether cos theta equals 0. Remember, we're restricted to angles between 0 and 90 degrees, or between 0 and pi over 2, if you prefer working radians, because that's the only physically meaningful case for this cone. It can't have an angle bigger than 90 degrees or less than 0. And in the range that 0 is less than or equal to theta is less than 90, there's really only one place where cosine of theta is 0, and that is at 90 degrees. All other places cosine has some positive value. And the angle being 90 degrees is sort of madness, because then it will make the radius 0, and therefore the volume would be 0. So that can't be our maximum. So that's really no good for physical reasons. So then we go over to the other side and we say, how about if we have cos squared theta minus 2 sine squared theta being 0? And we do this by sort of, well, I guess we want to do a little bit of trickery, because generally mixed trig functions and equations is bad news. It often leads to transcendental equations that have, by definition, no algebraic solution. So I want to reduce this to being only one trig function. And the way I'm going to do that is I'm going to replace cosine squared theta as 1 minus sine squared theta. It doesn't really matter which of them we replace, but we definitely want to replace one or the other. And I'm just going to do this because it's less to multiply if I take the thing that has a prefactor of 1. And so putting all of that together, we get 1 minus 3 sine squared theta equals 0, or 3 sine squared theta equals 1. This means that sine squared theta is 1/3, which has two possibilities. When we take the square root, we have two possibilities, that sine of theta is 1 over root 3, or sine of theta is minus 1 over root 3. However, we are still in the first quadrant between 0 and 90 degrees, and sine is never negative in that quadrant, so therefore this is also not a physically meaningful solution. Therefore, we're left with just theta is the inverse sine of 1 over root 3, which our plastic pal, who's fun to be with, will tell us that this is just about 35.2 degrees. So that would be the angle that gave us maximal volume for our cone.